Okay, for the last lecture of the structures portion of 347, I want to just go through and review each of the elements that we talked about: slabs, beams, columns, foundations, and go through very quickly a review of the process for designing each one of those and the tools that we use in each case. There will be a PDF of this, as there are of all of the lecture slides on the Canvas site. So this is one-stop shopping. You should be able to come here and get almost everything you need to do the calculations and the sizing for the final assignment. I'll go through these relatively quickly. All of them are covered in more detail, of course, in the lecture videos themselves, and you can go back to the YouTube channel and review these anytime you want if anything is a little bit unclear. So just to go through the process, we'll look at slabs first, go through again some of the charts that we use to size those, go back and look at the process for beam design, shear moment diagrams, the section modulus, steel tables in particular, and the iterative way that we figure in the dead load. Same applies for girders, and then we'll look at columns, slenderness ratios, the column tables, and then finally foundations, just the very simple load and area calculations and the soil tables that we use to figure those. So to start with slabs, the first thing we look at, and remember that when we're talking about slabs, we're hoping that we can make them perform like two-way systems. So redundancy in load paths, loads that are transferring in more than one direction, that therefore allow us to take advantage of this synergy of the two axes. If we're resisting deflection in two axes, we're getting an exponentially greater resistance to bending. And when we do this, we're trying, where we can, to get bays that are more or less square. Those are going to be the most efficient. Remember, too, that we're looking for stiffness and strength, but we're also looking to save weight. So a thin slab is going to deflect too much. A solid slab is going to be too heavy. We're going to get problems with punching shear. And so we're looking for ways to have a maximum depth of the system, but to have as much air in that system as we can. So we use things like one-way joists, where the slab is basically sculpted into what looks like a set of beams monolithically connected to a very thin slab, or looking at things like waffle slabs, where we're literally taking out most of the dead weight and leaving a network of joists in their place. We do use flat slabs, but when we do that, we get into heavy enough situations that we have to worry about punching shear, and we're either dropping panels like this, or we are just heavily reinforcing them with a lot of very expensive steel reinforcing. When we size slabs, we are looking at the charts. The charts are taken, in our case, from et al. And Studio Companion, and we're comparing systems, looking at two-way systems, knowing that we may need, when we get into the finer details, our structural engineer may tell us that we need things like drop panels or column caps to resist punching shear. And then whether we're integrating mechanical systems, worried about weight, trying to get the maximum span, or looking at the cost of complex formwork, we're deciding the system that we're going to use. If we have if we have a rectangular bay, then we're looking at spanning the short direction with our joists as well. So the charts, remember, we have a span typically at the bottom, and we're going to have information about the depth and what that depth is composed of going up the vertical axis. So here, for example, if we want to have, say, a 12-foot span, we read over 12 feet is about here. We go up, we can do this for roof decking at 3 inches, but really we're probably likely to have a 4-inch deck if we're trying to get over 12 feet. Joists, a similar table. Note that we've got 2x6, 2x8, 2x10, 2x12, and then here we have typical spans for those joists. Depends a little bit on the species. We're almost always working with strong woods when we're doing wood framing, so something like southern pine or Douglas fir or oak. We have these charts as well for concrete slabs. So notice that we have a difference between solid flat slabs, which take relatively short dimensions and are relatively thin, and then hollow core slabs, which function, remember, like monolithically connected I-beams. basically a way of tricking the slab into working more like a two-way set of deflection-resistant beams rather than just a solid flat slab. When we get into flat plates, here notice that we have a difference between conventional reinforcing, which is what we'll mostly use, and post-tensioning, which we do in extreme cases, parking garages, things like that. Expensive process, but as you can see, it gets us about double the span for the same depth. We have depth of slab over here, and because these slabs are so heavy, we also have a chart here that shows us what the minimum column size is to prevent punching shear. When we do steel framing, we start with a steel deck. Poured in place concrete goes onto the steel deck, and here notice we've got span across the bottom, and then total depth of slab and the dimension of the decking itself. So all of these assume that we have a 2 to 4 inch slab on the top, and then the decking, which is off the shelf, those are in standard sizes from 1 inch up to 3 inches. More complicated concrete systems include one-way joists. Here notice that when we're looking at the span, we get information on both the total depth of the system, from the bottom of the joists to the top of the slab, and also the depth of the voids in between the joists. And in here, we're almost always talking about basically a 4-inch topping slab and then joists that are anywhere from 6 to 20 inches deep. Again, we've got the option to post tension if we're in an extreme situation, but we won't do that for most conventional spans. Waffle slab, everyone's favorite. And here notice again that we do this both in terms of the height of the void, the dome formwork that's sitting on the scaffolding forming the actual joists, and also the total depth. And again, we're assuming usually about a 4-inch topping slab, and then whatever the depth of the pans are. Here again, we have minimum column size going down the right. So that again is to avoid punching shear. Notice that we may also fill in some of those voids. We may leave some of the domes off of the formwork so that we get nice big shear panels around the columns. We then come to beams, what slabs frame into, and here we have a slightly longer process to go through because we have to figure out the loading on the beam. We then have to go through and we have to figure out, based on the section modulus, whether we've got sizes that can carry not only the load that we're putting on them, but also their own dead weight. And remember that we do this by first finding the external equilibrium, figuring out what reactions we need to stabilize the beam giving its loading condition, and then sort of zooming inside and doing the shear moment diagrams to figure out what's going on inside the beam, how those exterior or external forces are being balanced by internal stresses. So here's our process. We'll first use rotational and vertical equilibrium to find beam reactions. We'll go to either the table of formula, which I'll show you again, or we'll draw our own shear moment diagrams to find the maximum bending moment and maximum shear. For simply supported beams, remember maximum moment's usually going to occur in the center. Shear almost always occurs at the end. And then we'll use the simple flexure formula, maximum moment equals allowable stress times section modulus, to back out of there a figure for S, the section modulus, a measure of the cross-section's area, and where that area is relative to the neutral axis, how efficient the beam is at resisting bending. And then if we're working in steel, which we'll typically do for these examples and for the lab assignments because they make it easy, we'll look at the steel tables. If we need to, we can work backwards through the section modulus formula to figure out a beam size. And then remember that we have to rerun these 4 steps, including the self-weight of the beam, adding a distributed load that will be the pounds per linear foot. Again, from steel designations, we can get this quite easily, the second number of steel designations for W shapes, to make sure that the shape that we've picked will carry not only the load we're putting on it, but also the dead weight of the beam. We'll use maximum shear equals allowable stress in shear times cross-sectional area to check that we're not exceeding the maximum capacity of the beam in shear. This is a rare thing except for short beams and heavily loaded ones. And then depending on whether we have a deflection criteria of L over 240, relatively loose, or L over 360, relatively tight, we'll use the deflection formula again from the tables that I'll show here in a minute to check for a compliance with deflection. So remember that shear is the tendency of materials particles to slide past one another. Just like kitchen shears, we're slicing the beam, we're basically sliding one half of it past the other. Bending is what happens when we carry a load over a span and we get a pair of internal stresses. Tension usually on the bottom, but in multi-bay beams it can be at the top over columns as well, and compression on the other side of the beam from tension. And then these are mathematically linked through shear moment diagrams. And remember, we drew through these using the figuring out the reactions, sort of telling the story, right, or doing the thought experiment to think about the internal stresses that the beam needs to develop so that a free body, no matter where we slice it, will balance whatever external loads we see on that free body with an interior stress. For a single load on a simply supported beam, shear diagram looks very simple like this. And remember that the value of the shear diagram equals the slope of the moment diagram, and the moment diagram will peak or valley, both places are things that we're interested in, wherever the shear diagram crosses zero, right? This is what we call the inflection point. When we have a distributed load, we remember that we take the reaction, and then each one of these infinite number of small arrows will push the shear diagram down a little bit. Or you can think about it that by the time you get to midspan, the distributed load here will be equal, if it's symmetrically loaded, to one of the reactions. So we go up a reaction, and then we gradually reduce the internal stress needed to balance that reaction until the middle. The slope, again, of the shear diagram equal to the value of the moment diagram. The value of the shear diagram is equal to the slope of the moment diagram. So here we have a very high positive, gradually tapers off to zero. So there's a summit, a flat spot right there. And then we get a negative that gradually tapers off to a very negative, very steep slope at the end. So this is a classic set of shapes for a distributed load, simply supported. We have a bow tie here, and we have a frowny face or a rainbow, whatever you want to call it, here. Remember, too, that the value of the moment diagram equals the area of the shear diagram up to that point, right? Because this is the reaction times a moment arm. So here we have the reaction, we're timesing that by a moment arm, and that gives us the area or the value of the moment diagram here. So we're going to take the area of that triangle to tell us what the maximum moment is at the inflection point. Fortunately, for simple situations, we have a lot of formulas that we can use to sort of shortcut this, figure out the maximum moment. So for distributed load with simple end supports, maximum moment is just WL over 8, and that is W, the total load. So we have to sum up the distributed load and treat that as a single load, figure out what the magnitude of that is. We multiply it by the length and we divide it by 8. And we've derived this from the geometry of the two diagrams, but this is a sort of handy way to remember it. We also have formulas for maximum shear, and in some cases, simple loading cases, maximum deflection, which I'll come back to here in a second. If we're designing in timber and we need to, we can use formulas to find section modulus, but in steel, we're lucky that the steel industry has given us the moment of inertia, section modulus, radius of gyration, cross-sectional area, everything you need to do the beam calculations. So here from an old table. And the other thing that we need is maximum allowable stress. So we have that here in this chart for typical construction materials, the maximum allowable stress for A36 steel, 22,000 PSI. That one's worth remembering. But you can see all of those are listed there for the materials that we're likely to use. That table also has information on the material's stiffness, modulus of elasticity. and we'll come back and we'll use this when we do our deflection calculations. Section modulus table that's most useful, at least to begin with, is this one, where we've listed section modulus increasing, and when we find out what the section modulus is we need to carry a given bending moment, we'll come over here and we'll read down until we find a beam with a greater section modulus capacity than what we're asking it to take. And we'll want to give ourselves a little leeway because we know that we're going to be adding the weight of the beam back into the equation. We'll come back to this. We'll use the weight of the beam per linear foot, run the formulas again, see if it works, and if not, we'll go down further on the list to find section modulus. Here, another version of it, section modulus isn't listed in rising numbers, but we have other charts that show us the cross-sectional area that we'll use to calculate the beam's resistance to shear. Okay, those beams all sit on columns, and for column design, remember that we're basing the design on the tributary area. So we're dividing up floor plates based on column locations. We're assigning basically every column a way to think of this as a fair amount of the floor. So if we have a rectilinear grid, we're basically drawing lines at the midpoint between any two columns and then assigning each column a tributary area based on that. Remember that in tension, we only have one mode of failure. Columns are in compression, which means that we have to design them against crushing, which happens for short columns, hockey pucks. For architectural columns, any column with any amount of length at all, especially if the effective length is greater than 50:1, and that is a measure of the length versus the radius of gyration, the average radius of the column, then we have to worry about the column failing in buckling or bending. These really, if we want to get technical about it, are beam columns because they are carrying not only an axial load, but they are also carrying a bending load. And the further, once that deflection starts, the moment, remember, gets bigger and bigger and bigger as that deflection gets greater. Greater moment causes greater deflection, and we end up with this vicious cycle where eventually the column collapses. Fundamentally, we are looking for rotational symmetry in our column shapes because we have to design for the worst case. In beam design, remember, we're looking at the deepest possible beam in one direction, right? The section modulus in its best case, because we know which direction the load is coming from, but we don't know which direction a column is likely to buckle in. And so we tend to be looking for shapes that have rotational symmetry, or we could say a radius of gyration that's equal in every direction. In reality, we'll often use W shapes, but there's a special family of W shapes called compact sections that makes for reasonably good columns that doesn't have a huge discrepancy in the radius of gyration around one axis or the other. So to size a column, we take the load from the entire tributary area. We figure out how the column is connected at the top and bottom. And remember, we get a discount if we have fixed connections over pin connections. We multiply the column's actual length by its K factor to get its effective length. And then we use the column tables, which allow us to look up the effective length. We always round up. And then we go down that column and find an allowable load greater than the one that we've calculated. We read across that to find the column size. Remember that we are designing for different loads at every floor in a building. So the top roof load may just be, as we saw, something like on the order of 50,000 pounds, but on the bottom it may be 10 times that. It may be something like 500,000 pounds in a 5 or 6 story building. And we are trying to stack them directly on top of one another, trying to avoid transfers, trying to avoid eccentric loads on columns where we can. So here is our effective length chart. And remember that our standard baseline condition is a column that's pinned at the top and bottom. So that has the full range of deflection. And when we fix one end or both ends, we get to take a discount. That's the practical number down here that allows us basically to shorten the column. Right? The column is going to behave like one that is 0.8 as long if we fix one end and 0.65 as long if we fix both ends. And this has to do with controlling the curvature that the column takes as it is deflecting. So we come to our column design chart. Here we've got one for steel, and we go across and find the effective length. Once we get our effective length, we read down to get an allowable load that's greater than the load that we're putting on it. So here, 10 feet, 11 feet, 12 feet, these are floor to floor heights. And once we get the one we want, we read down, and these are in 1,000 pounds until we get a number that's greater than the load from the tributary area above. And once we do that, we can read over, we find the column shape or size that the steel table is telling us, and we're done. This already takes into account the dead weight of columns. And then finally, we talked about what those columns discharge their loads into, the foundations, the pieces that spread the load from that column out over a safe patch of ground. We talked about soil mechanics and how we are typically looking for soils that are both strong in themselves, but also have rough surfaces, and therefore can bear directly on, the particles can bear directly on one another, but they also have a kind of friction fit, and they form effectively a kind of solid base underneath our foundations. Poor soils, on the other hand, are basically fluid, and they will flow under pressure. We want to avoid these wherever we can. Somewhere in the middle, we get soils that are pretty good, but maybe need to be remediated, compacted, something like that to work. So we talked about low-rise footings, slab on grade, mat or raft floating foundations, and then spread footings, which are most common under walls and columns in low to mid-rise construction. We talked about the way that these spread footings distribute their load. That's very analogous to the way that slabs collect loads. And so what we're worried about is both transforming, in this case, the exact opposite, taking the point load of the column, spreading it out over a safe area. But we're also worried, just as we are in slabs, about punching shear and the need to provide often a shear panel or something that increases the intersection between the surface of the column and the section of the footing. For high rises, caissons are probably the most common, most reliable footings for skyscrapers, but we discussed the fact that we can use the friction of fluid soil to develop resistance to the load through friction piles, and in this case column caps, so a way to collect all of the resistance of those piles and use them to balance the load of the columns. And in rare cases, in sort of mid-rise buildings, we can actually use displacement foundations with some stabilizing elements to literally float a building in the soil. And foundation sizing, very simple. We use the same tributary area that we use to find the lowest level column. That gives us the total load on the foundation. We take the soil survey that a geotechnical engineer has given us, and that will tell us the allowable load per square foot of soil at every stratum down 50, 60 feet. And for each of those strata, we'll figure the allowable load that we can put, or the load that we want to put on the foundation. We'll compare that to the allowable stress on the soil, and we'll get an area out of that, a safe area that represents the distribution of that load over a safe amount of soil. The way it usually works, the shallower strata are generally weaker, so we always have this trade-off between very, very big foundations at shallow levels and very, very tiny foundations at deep levels. And that will, along with knowing the cost of excavation, the area conditions, the areas available to us on the site, that will help us make the decision balancing the depth of excavation and the size of the footing. So here's our allowable bearing loads on various soil types. We tend not to build on things like silt and clay. and fill unless it's a one-story building. When we get into gravel, we're pretty happy. 6 to 8 tons per square foot is pretty good for a mid-rise building. And when we're talking about skyscrapers, we are really doing everything we can to get down to rock and to take advantage of the very high bearing capacity of bedrock in particular. Okay, that is a very, very hasty review of what you'll need to size elements throughout your building frame. Notice that you also have these now in your back pocket for studio. So going forward in studio, we'll expect you to have, if not fully calculated elements, at least some idea of how large the elements in your studio project ought to be. When we come back in ARC 348, we'll take all of these elements and we'll look at the synergies that occur when we put them together. What happens when we attach columns and frames in ways that allow them to share some of the bending load or share some of the lateral load? Frames are a way of thinking about the way that we can build up resistance to gravity and to lateral loads into an actual coordinated system instead of just individual elements. So good luck with the final, good luck with the environmental module, and we will see you again in spring.